Hi friends, I want to talk about records this week, and one of the records I'm really excited about that I found in my collection is this original Motley Crue Too Fast for Love album. This is on the Leather Records label. This was their label before they signed to Elektra. And this is one of about 900 copies that are in existence. And if you look on eBay from time to time, you see these come up for sale on vinyl. And they're worth quite a bit. But that's not the kind of record we're going to talk about. C++ records enable us to take simple data types, strings, integers, doubles, whatever, and combine them together into a single unit. And in doing so, we create a new data type. Say we want to collect information about 10 different students. If we were going to write a program using the knowledge that we have right now, we would create maybe an array with 10 strings in it, and it would be student 1, student 2, student 3, student 4. But then if I wanted to collect the GPA of those students, then I have to have another array that says GPA 1, GPA 2, GPA 3, and then I would have to maintain the parallel state of all of those arrays, and it would just get very confusing. What a record allows us to do is to take the string for the name, the double for the GPA, the integer for the student's age, whatever it is, and combine all those together into a new unit. So we create a new data type called a student. And then I create variables of that new data type, and that allows me to collect all of the information about a student in one place. I think you're really going to like this, so let's follow along.
The C++ keyword that implements this structure is struct. And as we declare the struct or the structure, we are creating a new data type, as I mentioned before. This new data type starts with the keyword struct and is followed by a legal identifier. So struct name will become the name by which your program knows the new data type. An opening brace is followed by a list of simple data types or complex data types that we'll get into later. So data type 1, data type 2, whatever you choose for your design. The list of member data types is followed by a closing brace and a semicolon. That semicolon is the most often forgotten part of this and will cause your compiler to kick out an error. So here's an example of the idea being implemented. So we have student data. So we have a new data type called student data. The members of that new data type are simples that we already recognize. We have two strings, student name and student ID, and a double that contains the student's GPA. So once we have declared that in our program, and most often we would declare this in the global scope so that all of our functions recognize the new data type. Once we have declared that data type, we have to put it to use, and that means that we have to declare variables of that data type. So once we have created the data type, we declare variables just like we do with any other simple type. So student data, and the variable is going to be called new student. Now if we want to work with new student, we use the member access operator, which we're going to refer to as the dot operator. So when we want to work on the individual members of the new student variable, we say the identifier new student dot and then the name that was applied to the members within your structure definition. So student name, student ID, GPA. And then we do just any other operation that we would normally do upon those data types. So you see in this example we are assigning the student's name King Josiah, the student ID KI344, and the GPA 3.6. So any legal operation that you would do upon those simple data types, you can do within the structure itself. So we have now assigned all of those into this structure. We can also work upon the structure as a whole. So if I want to copy all of that data that I just assigned in the previous example to another instance of this data type, I simply use the assignment statement and copy the entire structure into another structure of the same time. If we're going to operate, if we're going to do operations such as comparisons, things of that nature, those have to be done on the individual elements. There are no operators that work upon structures as a whole. When we talk about arrays and structures, sometimes the question will come up, why not just use an array in place of the structure? And the base answer, the foundational answer, is that the array can only contain a single data type. Even though it can contain a virtually unlimited number of elements, it can only contain one type of element. The structure can contain any number of types of data types. In addition to that, the array can't be returned from a function, and it can only be passed via reference, and there's some limitations there. Whereas the structure can be a return type from a function, and it can be passed by either value or reference, whatever is appropriate to your program. We can also use structures as the base data type for an array. And by that I mean we can define a new data type, in the case of the example you see before you, student data, and then declare an array of those structures. So if you can kind of picture that, each of those little packages of student data, the name and the student ID and the GPA, are all now present in each one of the subscripts of the class list array. And if we want to address them, we still use the member access operator, the dot operator. And we pass the, as you see in the second line there, we pass the name of the array, the subscript, and then put the dot operator right after the subscript, give it the member element that we want to access, and do whatever it is we need to do on that data element. We can also do something interesting in adding an array as a member element of a structure. So as you see in this example, we have added an array that contains all of the student test scores. So now I don't have to have a parallel array that just contains test scores. I can add that array into each of the structures. So student first name, last name, ID, and then an array of, let's say, 10 tests contains the score that each particular student has scored on those tests. In doing this, in structuring a record in this fashion, I have created a situation where all of that student's data stays together and moves with that data. And as I operate, let's say I loop through the student array, I can real easily now calculate average scores, highest scores for not only the student, but for the class as a whole. And it makes my operations much simpler. When I use this combination of data types and data structures, I can create a situation in which the data structure that I define maintains information about itself, so it becomes self-documenting. Think about when we're operating on arrays, and especially when we get into a situation where we're going to do some kind of looping with an array. Most often we need the size of the array. And so we end up passing the array and the array count back and forth through function parameters. In the case of passing an array into a function where we modify that array, delete something or add new, then we have to update count. We have to return that from the function or pass it via reference. There's a lot that's contained there. The structure will allow us to encapsulate information about the object. So in this case, we're going to create this structure called list type. And what it's going to do is be a container for an array, a list of items, whatever those items might be. In this case, it's integers. I'm going to encapsulate with that list the number of elements that are in that list. So now when I work on that list, I can assign, as you see in integer list, this example in front of you, I can assign, let's say, the value of 13 into subscript 0 and increment right then and there the length of the list. Now, because that's self-contained, every time that I operate upon integer list, I know exactly how many data elements are in there. And so again, I assign 37 into the next subscript, add one more to list length, and so on. Well, now you're saying, what does this do for me? Well, if I self-encapsulate all of that information, then I can pass just the single item, the list that I want to operate on, and then I can do any kind of operation that I want. I don't need to worry about where the count is, has it been modified, whatever, because the count and the data elements that are counted are contained in the structure that I'm passing in here. So if you look at this example, if you look up in the signature, we have sequential search, I believe is this function. And I'm going to pass in the list, the array the structure that contains the array of integers plus the count of those integers, and then the item that I'm searching for. So I've left off the parameter of the count of the list. As I go down and work upon it, look in the for loop below there, you see that I can use the list length contained in that object to control the loop, and then I can simply go and search for my item within the for loop, returning whether it's found by giving the location or returning -1 that tells the program that the item was not found. This kind of gives you a little glimpse of what object-oriented programming is about. In OOP, we design structures that contain both the data items and those functions that operate on the data items into a single container, into an object. And then we move or utilize that object and all the data and the functions travel along with it. So these are just a few of the uses of structures. In the next video that follows, we're going to talk about some really cool usage. Well, by now I imagine you've thought of a half dozen uses for the structure. And your programming assignment this coming week should give you some good experience in using the structure. I want to present to you the idea of, now that you have the ability to group data elements together, we also can embed structures within structures. And that allows us to create very, very complex data elements, but not so complex that they're not easy to work with. When we group data, as we talked about with the student exams, that package of data then travels along with the student. If we think about some other real-life objects that we might need to model, a lot of objects have multiple instances of those types of lists, multiple scores, multiple classes that the student might take. All of these give us an opportunity to create substructures that we then embed within larger structures. Since we're talking about records this week, let's look at the information that is necessary to describe a single record. We have the name of the band, and in this case, the name of the band and the name of the album are the same. This is by the Outlaws. But then look, we have a list of songs that are contained within this album name. So, there goes another love song, song for you, blah, 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 blah. We have a record label. We have a year in which the record was released. And then we have a list of the musicians that are on the album. So if we look at this and we wanted to model this, we see that it's an ideal candidate for a structure. When we look a little bit closer at the data, we find that we can organize that data into different subsets or be thinking structures here. So the band name stands on its own. But then the album information, that's separate because that describes the record. And then there's going to be one or more songs on every album, so that is another subset. And then the musicians that are on that particular album may change as well. In the case of the Outlaws, it's changed quite a bit since I think half of those guys are dead now. Okay, so we have these different subsets. We want to be thinking about how we can organize these into data elements. So in this case, we take the band name, that's a string, the artist, the title, the label, the release date, all those can be captured as strings. But you see the different colors on the data elements on the right there. We can create a structure, say for album information, and within that structure have artist, title, label, release. We can create another structure called song or songs. And then have title, composer, length, whatever we want to record about the song. And then again, another structure for the musicians, and we give their name and the instrument that we play. And this is what we can do with that. So reading from the top down, you see we have a structure called album info, and the order in which we define these is important, because remember that your compiler is going to read from top to bottom and from left to right. And in order for it to recognize something, it has to have already been declared. And the same is true with structures. So we have a structure, album information, and we have artist, title, label, release date, semicolon, close that off. Song information, same thing. Close it off. Musicians, close it off. And now here's where it really gets cool. We have a new structure called album. And within that album, I am going to embed instances of each of the first three data types. So you see that I have a variable called rec underscore album, and that is of type album information. And then I have an array called song list, and that each of those elements of the array is of song info. And finally, another array called players that is of type musicians. When I want to work with this, I will go one step further, and I will declare an array of type album, and the maximum number in the array will be the maximum number of CDs. So whatever 3,000 or 4,000 CDs I've got, that's how many I will put in this. The dot operator works the same. You just have to go a couple layers deep. So if I want to get to, let's say, Huey Thomason's name within the album information, it would be the album structure, and then I would drill into the players array, find Huey, and then I would go Huey, get his name, and find out that he is a guitar player. Now this is a bit beyond what we're going to be doing just now, but it gives you an idea of how the very simple data structures that we're working with right now can be combined and make it really easy to model very complex real-world information. Well, there you go. You know everything you need to know about structures, at least to get started on this week's program. Good luck with your program. If you have any questions, leave me an email or leave a message in the student questions forum, and then everybody can benefit from your question. Good luck, and let me know if you need any help.